So in this video, we're going to be doing an introduction to the continuous random variables and looking at the continuous distribution. So these are looking at probabilities for when the distribution is continuous. Now, if you remember before, we talked about how there were two different types. So there were discrete numbers and discrete variables, and then there were continuous ones. So when we've been looking at the binomial distribution and some other ones, we've been looking at discrete variables. So discrete means they have to take an actual value. They are not measured, but rather they take a certain value. However, now we're looking at continuous variables. So continuous variables are things such as height. So a good way to think about it is that height is like a spectrum. You have over here, let's say you have 200 centimeters, and over here you have 100 centimeters, and you're placed somewhere along here. Now you may say you're 175 centimeters, but you have to remember that is an approximation, because if you are 174.9998, you would say you're about 175, but technically you are actually this amount here. And so that's what continuous variables are, in which they normally they're rounded, so you can sometimes it's tricky to think about them as discrete, but actually they're not specific numbers, but rather they lie on a timeline. Another example is time. You may say 2 seconds, but that's like a rounding amount. It could have actually been 19987. However, just going back to discrete, if you're looking at number of goals scored, then you can't have in one match you can't have 1.254 goals scored. It's either 1, 2, 3, 4, or 5. So they take actual amounts. And even when you look at an average number of goals scored, it's going to be a specific number. Even though it may not be an integer, it's going to be an exact number. So looking at an example of a continuous distribution, looking at the frequency and sort of height. So this is a sample of a class, and we're just looking here at the height of a classroom. So we have some ranges, and then we have the frequency, or this can be referred to sort of the number of people or number of students. So here you have everyone between 140 to 150, but not including 150, so there's one person, and then you can see you go along here. So you should have done these in previous years, but this is some revision to get it back. So then you can draw a graph where you have the height, and you have 140, 150, 160, 170, etc. And in here you have the interval, and then the frequency, you plot the frequency, and you get a graph such as this. So this shows us the frequency, and this is continuous distribution because we're referring to height. But the main thing is that you can't have a specific value. Rather, we have these intervals. So we're saying everyone between these two heights. We're not saying everyone who's 141.2346, etc. But rather we're using intervals. And that's what we have to use for continuous distributions. You can't just pick about specific values, you have to use intervals. They could be very small intervals, such as 140 to 140.1, but they still do have to be intervals. So you've got this frequency and you've got the height, and then we've just plotted it here. Now this can relate to probability, because if we look here, I've summed up the total of all the frequencies. We found that there was a total of 40 people. Now, what is the probability that if you randomly pick someone from the class, they'll be between 140 to 150? Well, the probability is just equal to the number of outcomes, like the positive ones that you want, over the total number. So it's just going to equal 1 on 40. And then if you said, what about everyone between 150 and 160? Well, not including 160, it'd be 7 on 40, etc. And if you added them all up, it would total to 1. Another way is if you said everyone less than 170, then you'd go 15 plus 7 plus 1, which would be 23, and then divide that by 40. So you could change this to probability. So you could put this one here, sort of as a probability. Divide all these numbers by 40. and then you have a probability distribution with the height and the relative probability of these class intervals. So this isn't the normal way we're going to show continuous variables, but it is a good way to show you how that they have to be in class intervals. They can't be specific, and how you can see that they can be in a graph form. Now these are class intervals, however we're going to now use functions to describe continuous variables. So a common way to show continuous variables is to make them into a function and then graph it, and the area underneath the graph refers to the probability. So we're using a hybrid function here. So what a hybrid function is that it has this sort of thing, the symbol, and then it has 2 or 3, or it has multiple formulas, and then this bit here refers to what parts of x the formula refers to. So this refers to the domain of each of them, and then this refers to the formula. So at the moment this is 0, but you can also get piecewise hybrid functions in which you have multiple other formulas which you've encountered previously in methods. So that's the formula and that's the domain. And then this is what we'd call a probability continuous function, and the area underneath is a probability. So I said that before, but I just want to emphasize it. So the area underneath the graph refers to probability. So if we graphed this function here, we would have intersecting at 0, so it's x on 2. When x equals 0, the function equals 0, so we have 0, 0. When x equals 1, then fx equals a half, so we're about here. And then when x equals 2, fx equals 1, so here. So we have a straight line that looks something like that, where here is 2, 1, here is 1, half. And obviously you don't have to draw in all the points, but you do need to draw in the endpoints. Now these are solid dots because, as you can see here, it's equals to. So that's pretty important. You see the equals to, and that's solid dots. Then you look at 0 elsewhere. So that comes down. So this isn't there's no line in between these two. I'm just doing a dotted line to help show you. And then this is an empty circle because it's not included. And then it's 0 everywhere else. So the graph goes like that. Then from here, it goes along here. And now obviously at 0, the area underneath the graph is just going to be 0 because it's touching the line and it's going along the line. And so that's why you see a lot of hybrid functions for the probability that look like this. Because the 0 elsewhere is very convenient in regards to the probability doesn't matter along these ones. We're only caring about here. But you can't just write that because that's not mathematically correct. So you do need to put in the 0 elsewhere. So you have the probability, and then this is sort of x. Now this example could be referring to something about 0 to 2. And then this could represent graphically. So this is obviously a straight line, so it's pretty simple. But you can get more complicated graphs to represent different variables. So if we're talking about the previous one with the class intervals, you could have made a graph fx that looks something like that, with the probability here equaling 1 to represent the class intervals for the height, and you could calculate it like that. So we've got this, and then we know there are 2 important features of here. So I've already said this, the area underneath is a probability, but therefore the area must always equal 1. So the area must equal 1. And that makes sense because the probability so the total probability must equal 1, so therefore the total area must equal 1. And it can't be less than 1 and it can't be more than 1. So the area must always equal 1. And sometimes they may give you a question in which they have a variable here such as a, and you have to calculate it for it to be a probability function. And for that to happen, you need to make the area equal to 1 and then solve for whatever the unknown variable is. So that's 1. So that's area equals 1. So the second part is that the probability must be positive, because you can't have negative probability, so therefore the graph must be positive. Now, that doesn't mean the x-values can't be negative, because the x-values don't refer to the probability. The probability refers to the y-axis, as you can see up here. So we're looking at the y-axis, and this satisfies that. But if you had a graph that looks something like this, in which you have a negative x-values, then it couldn't be a probability function. So they're the two determinants that you have to look at, and both of them have to be satisfied for a graph to be able to represent a probability continuous function.